here we have a copper shaft that is subjected to axial loads. We can see that the axial loads are equilibrated, so we have 7 kips going to the left, the same thing as 7 kips going to the right, so the system is in equilibrium. But we are asked to determine what is the displacement of this end with respect to end A. And to do that, the first thing that we need to find out is what is the distribution of the axial load along the shaft. So for that, we are going to draw the axial load diagram. And we are going to start on the left. So I hope you can see that if we make a cut just a little bit right to A, we are going to see that that shaft is subjected to a tensile load of 6 kips. So in our axial load diagram, we are going to put everything that is in tension on the upper side of the diagram, everything that is in compression on the lower side. So remember, we adopt as a positive sign convention a tensile load and a negative sign a compressive load. We have 6 kips going to the left, so that means it's going to go 6 kips up on the diagram. As I move to the right for the next 50 inches, there is no load, so that load is going to be sustained at 6. And then at 50 inches from A, we have a 4 kilopounds force going to the right, so therefore we are going to decrease those 6 by 4, and we end up with 2 kilopounds. It's still a positive value, so the tensile load at B is 2 kilopounds. We continue going to the right for the next 75 inches, and we see there is no load, so we maintain that load of 2 kilopounds. And then at point C, there is a load going to the right 3 kips, so therefore we are going to decrease that 2 kips by 3, and we end up with -1 on the negative sign, which means that to the right of C, the shaft is in compression. As we continue moving towards D, there is no load, so that -1 is sustained. And finally, we close the diagram with the 1 kip going to the left, which means the entire system is in equilibrium. So now with this diagram, we can see that the segment AB is under a tensile load of 6 kips. Segment BC is under a tensile load of 2 kips. And segment CD is under a compressive load of 1 kip. Once that we know the distribution of the axial load, the displacement of one end with respect to the other end of the shaft would be just the addition or subtraction of the corresponding elongation or shortenings of each segment in the shaft. So we apply the formula for the elongation due to an axial load, elongation or shortening, depending on whether that axial load is tensile or compressive, times the length over which that load is applied, divided by the axial rigidity, which is the product of the elastic modulus times the cross-sectional area. So we are going to then decompose this shaft into the 3 segments where the load is constant. So therefore we have the first segment would be the load AB, which is a tensile load. The second segment is the load BC, which is a tensile load as well. And finally, the load CD is a compressive load, so when we would substitute, we would have here a negative value. We have the length of each segment, and is divided by the axial rigidity, which is the product of the elastic modulus times the cross-sectional area. The elastic modulus for the entire shaft is that of copper, which is 18 kSi. And then we need to determine the area of each segment. I have put it here on the left. So they are circular solid cylinders. So we have the diameters. So it would be just the pi diameter to the square divided by 4. And we have here the values, and then we just substitute into the formula. Note that for the tensile loads we have a positive value, and for the compressive load there is a negative value. we do the algebra and we find that ND displaces 0.000767 inches from A.